Right. Okay, so hello everyone. I will close the door first. Wait, maybe not. Okay. So we're going to the stochastic course. Stochastic, just to say, is another word to mean random. It's just fancier. So we'll do some random stuff, but fancier. And yeah, I'll give it a shot. So before talking about making a small introduction and then listening to Gianmarco talk about an overview of magic theory, I will just give a few references, so you can find all of them, and we will try to make it online the page for the course on meet.ly. And I will put some online notes here and references as well. So the best reference for this course is this book by Evans, called An Introduction to Stochastic Differential Equations. It's very small. It's very easy to read. This is the best reference for the basics of stochastic. We'll do a bit more, but what's inside, in a way, more probability at least. And at the end of the course, we will do some numerical analysis and a little bit of stochastic differential geometry. So this is not in this book, but everything you need to know is here. For the stochastic part, I have to cite the ups and downs. I'm probably not pronouncing it properly. This is also a good book. It's a bit more complete, but more applied, I would say, to finance, especially. And finally, yeah, that will be all for the. I mean, I have another one that I will show you when I receive it. It's in my notes. For the part in probability, we will use mainly this book by Lebesgue and York, about the martingales in bone and motion. This is a fantastic book, and this one you can find in the library, but it's a bit advanced. Finally, for the measure theory, yeah, this one. So this one is red. It's the one that TJ used for his course. It's the one by Follon. I will leave also books here, so you can read them after the course. And this one that I can close.
This is the book.
Okay.
The following is much better for what we need.
Okay. The elements of integration of the net measure, but I won't go this one.
Yeah, and you use mostly that one.
This one?
Yeah.
Okay. I got to use the for.
It was a combination. It was a nice combination.
Okay. Well, anyway, we won't talk too much in measure theory. Then for the numerical part, I will use Stieltjes, Flatten, and Schultz. It's I don't really like this group, but don't stay. Hi.
Hi.
We were just talking about the reference.
I was wrong about my lecture. It was a 10, so I can come.
Okay.
I said, told you that I can come with my lecture, but that was assistant.
We can. I will talk about it in a minute. Okay. Then this book for the numerics. The Bible of numerics for SDEs is basically a book. Stochastic numerics for mathematical physics.
Okay. It's not counted.
No.
Counted.
This one is a bit old now, but I shouldn't say that now. I prefer this one. We will also use numerical integration of quantities a little bit. So if you don't know much about MFF, for instance, we'll talk about it at the end. I will use this book, geometric numerical integration. And finally, this is another book on numerics for SDEs, called free energy computations, but it mainly focuses on applications in molecular dynamics. So these are all the references we will use. You don't need all of them. I think the only one we need is this one. This one is fantastic.
Okay.
It's very easy. It's complete.
This is time. What does mean that you can download it for free?
Legally or not?
Maybe. No?
I don't think download it for free. Okay. So let's move to the references. Just we have to talk with day and time. Is Friday at this time okay for everyone? Apparently, it's also okay for Medina.
So we'll say 12:15.
12.
Okay, actually starts. You're welcome to show up earlier, but we'll start talking at 12:15.
Okay. Then I just have to talk about the exams. You can take an exam at the end if you want, for 10 credits. And I think we'll give you something enough to study for a project, maybe some programming if you don't want to. And then we'll listen to what you did and right, what you do really good. Okay, do you have any questions?
Is there a date approximately of the exam?
In June?
Okay.
I think that's okay. Okay, let's go on. So in this course, in the stochastic differential equations and derivatives, the goal is not to give the most general definitions of SDEs, but just to define them, give an existence and uniqueness theorem, and then give some applications. So in stochastic differential equations, we have stochastic, but as I said, we just mean random, and differential equations. So let's begin with this. Let's take dE of 4x prime of t equal to f of x of t. You know that you have to add an initial condition that it's well defined, composed. And you have this theorem that you know. I don't know how you will hear it, so the sheet sheets will be telling you off, but if f is globally Lipschitz, basically it's derivative of it, then there exists there exists a unique solution. It's okay. Now we'll not really use this formulation. We'll prefer an alternative formulation that is called the integral formulation. We can rewrite this problem with an integral. So it's x of t equal to x0 plus the integral from 0 to c f of x of s. So here you include the initial condition in this. So now what is the stochastic differential equation? It's almost the same, except that you have some noise. See, at the beginning of the, in the middle of the 19th century, a biologist called Robert Brown, he observed that if you put some pollen in a big pot of water, and you see that the pollen particle moves, even if there's no wind, and it moves in a very strange way. It's like something very irregular, and even if you leave it alone in the room, it will move by itself, even without any wind or whatever. And we had to wait till Lebesgue and Einstein's work at the beginning of the 20th century to understand that the collision of the particles, the collision of the water molecules with this pollen particle, was the reason that it moved a little bit and had this weird pattern in the water. This weird pattern is what we call the white noise. So this is I don't want to go too much about it because we'll not do this. But psi is some noise called the white noise. It's not a function, it's a distribution, so that's why we'll soon forget to look at it. And SDE is an equation x prime of t is equal to f of x of t plus g of x of t. So what is the define this thing? The problem is that this equation has a mean. So you cannot just multiply something by a random variable and then extend everything that's here. It doesn't work because this thing is a distribution and not a function. So in the following, we will see that this white noise, we will write it as W T. Again, everything is in here, it's just an introduction. And W is what we call Jordan motion. It's from the name of Jordan ground biology. All right. So now I could just replace. I know that W exists, but dW is d the derivative of W will see that it has no meaning. And this, I forgot. I will just show you some pictures. Sorry for these people on Zoom. Okay. Oops. No, this isn't working. Do you know how? Because I just cannot open the window. This is a bug with MATLAB. Yeah. Okay. Anyway, I will show something else then. Okay. So this thing that you observe in the water is something like that. Yeah. I hope you can see a little bit. Basically, you have some particles and they move randomly. So sorry, I have another simulation. Next time it will be more prepared. You see that these particles, they move randomly. It's not a smooth motion, something that is not differentiable. And each one of these particles it follows some kind of equation like this, where you have a Bonon motion. Basically, you have
There is something particular about it. You like
yeah, the F is not completely trivial. Yeah, anyway, when I will make it work, the other ones in the simulation, we'll see afterward. Okay. So the idea is then that we multiply everything by dt and we integrate, and then we will be able to make sense. So what we'll train is the root formulation of the SDE. This derives something like x of t is equal to x0 plus the integral from 0 to t of x s plus the integral from 0 to t of g of x dw of x. And now we will be able to prove that this actually makes sense. So I just multiplied everything by t and I integrate it. So now we can see the first points of the force. The first one is, what is that? What is the volume? The second one is, oh, this is just an integral. The integral that you know is the Lebesgue integral or the Riemann integral, whatever you prefer. It depends on the situation. This we don't know. It's the integral with respect to the Boron function. We will have to define that. This is called the stochastic integral. Finally, the next question is, does there exist a unique solution to this? In what space? Is it a random variable? Is it not? How does it work? So we just write uniqueness and the existence of solutions. So these are the three first points that we'll try to address, and then we'll talk about that. So as you can guess already, the point is to prove the theorem to form if F and G are Stieltjes, then you have a unique solution in a certain space with certain assumptions, blah, blah, blah. Okay. So what I want to demonstrate this is actually interesting. This is not just a straightforward extension of this. And for this, I have two examples that I actually am using. It will work once, then we'll have to do some work. So the first one is this one, you know, I write it as dx is equal to ax dt. And when I write this, I actually mean x prime is equal to ax. This we know how to solve this. The solution is x of t is equal to exponential at. Okay, so what we could assume is that if I write dy, if it's random, I write it capital letter, dy is equal to a y dw, then the solution, it should be y of t is equal to exponential a w. Well, turns out this is completely wrong for some reason. And what we obtain instead, what we obtain instead is w of t minus t of t. Minus t of t. For some reason. And so this is actually not hard to compute, not hard to see. This will equal to formula. And it's one of the reasons to study this, because you have some things that you're used to, especially the solution of a linear SDE should be just an exponential of something, but not something that crazy, something easy. So we'll see multiple definitions of the integral and see how they are combined together. We'll talk a little bit about graph test and how we can actually probability of that as well. Okay. About the applications, I just want to say a few words. These equations, you actually use everywhere. Before Einstein, it was not that popular, but now you can see them everywhere. From the stock market to just physics, especially molecular dynamics. And I mean, that's why we will also present some applications, because we want to be able to manipulate them, especially to create some small programs, MATLAB, Julia, whatever you prefer, to model the motion, solution of an SDE, and to apply it in different cases. And then we will see some stochastic differential problems. I think I will just stop here for the introduction. Do you want to come more?
So this was, I think, a very nice motivation for the course. Is there any part of this that you're missing? You haven't seen, some people haven't seen stochastic processes, some people aren't very, it's okay, because we're not going to take a step back, so slow down and fill out a lot of fundamentals. So the goal for the rest of today is to actually review the measured theory behind integration theories that you've seen before. But either maybe you haven't, or regardless, we need some sort of review, because as I hope it's clear from the other answer, this is somehow very unclear what it means. Like it operates, it's nonsense. Even if you're familiar with what W programming motions. So let's take a step back and begin. Let's not use red for recording. I review this because I want to make clear exactly the point where we're going to start at. So the notion here is that we want to define an integral form. Integral from A to B Let's write as simple as possible expression of this sort. In this case, what we do is at the real line. By the way, if at any point you have an issue with my handwriting, don't hesitate to stop me. I has a tendency to degrade over the course of me talking. We want to iterate this from some fixed real number A to B. What we do then is partition this one n. So I will call such a list where A is x naught is less than or equal to x1. And this a partition yes, where I take the notation that x0 and xn endpoints are actually specifically the endpoints in B. And on top of this, I'll introduce what I call a tagged partition. List of the same sort. Where we beyond just the partition, we also have a list. I'll call this T1 through Tn. That's the property. I'll say that this is a partition. Ti's are always in the interval xn minus 1 xi. So what does this do? So these TIs are a choice of points somewhere in each of these subdivisions. And we can set some notation here. Let's say absolute this n length and this maximum across I, the lengths of the subintervals, which we will call the mesh. So I want to set all of this notation to give us some hand tools for actually making sense of these intervals. Because when we go to actually write down a Riemann and Darboux, I mean, we're all familiar with the facts that it should be written somehow as a summation of these, right? We're going to say that this will be a function F and tag the partition P, that the Riemann sum is equal to first sum of I1. Or n here, length of the partition of f of ti. Next, this shouldn't be so bad. This is our sum, and all we're doing here. Is for each of these sub-intervals, we're imagining. Right, so on, where the height of this rectangle is determined by the value of the function at the tag. Yes. So when we take the Riemann sum, we're simplifying the area of rectangles. Nothing surprising. I want to be really precise about all of this because it turns out that both the choice of partition and the choice of tag becomes a very subtle thing as we head into stochastic intervals. but let's write down for first. Mission. Suppose for every epsilon greater than 0, there exists a delta equal to 0 such that for any partition with the mesh being controlled by delta, the difference exists a delta, I should go right there. Suppose, I mean, for this right here, I apologize. Suppose S is a number, and for any epsilon greater than 0, we have some delta, such that if you choose any partition whose mesh is controlled by delta, we have this property, that the difference between the Riemann sum and this fixed number S is less than epsilon. So it's an epsilon delta definition of what it's got. In this case, what happens? This is just the definition of Riemann. We say that F is Riemann equal. S is the Riemann integral of F right that the integral from A to B makes the x. Okay, so nothing, hopefully nothing's perfect. But honestly, the first time I saw this after I took the analysis course, it's actually surprising because this is not the original. This is not the definition that I saw in my technical literature course. So maybe this is familiar, maybe not.
I mean, when we actually now we say the sum over sum and the difference between the two of the zero.
That's exactly what I wanted to talk about. So I wanted to cover this. I wanted to make sure to make this explicit. So did you see this? This is actually what is called historically referred to as the Riemann integral. This integral is one I saw as well, or called the Darboux integrals. So there's a subtle difference here. Where's my eraser? So if you want to consider that, my sums. In practice, this sort of limiting definition is a bit of a pain to work with. So what's often presented is we define U of Fp for some given function f and some given partition P. The sum of the partition, where you take the supremum of f of I, and etc. Okay, I would call this an upper Darboux sum. Notice the difference here is that in the Riemann sum, in a tagged partition, the TIs are chosen ahead of time for us. In this upper sum, instead, we have just a regular partition. And in each subinterval, we choose the tag that makes this as great as possible. Then, of course, there's the analogous lower one. And inflow. Yeah, that's interesting. Is the subtle difference here clear? I apologize that I have a different notation for our partition and tagged partition. So in this first case, P, is what I refer to as a tagged partition. That means that the partition of the interval and I've chosen ahead of time TS. These tags. The tags determine where I evaluate the function. In this notation, what I'm saying is that I have a partition of the interval, but I don't have pre-chosen tags. Instead, on each subinterval, I choose the tag that makes it the supreme of the interval. Of course, it may not actually be achieved. If the function is continuous, of course, it's achieved.
Was explained if these two definitions are not equal.
They are.
They are.
They are, but it's not obvious. And I think understanding the subtle difference here and why it's not obvious leads us to being able to understand why stochastic intervals are natural. It's the same type of distinction. There is a conclusion that you're saying. So let me give a definition of Darboux. Actually, let me define it L and F. So I'll say UF equal the interval across all partitions of P and LF equal the supremum across all partitions of LF. Okay. So I have to consider all of the possible upper and lower sums. And I take the supremum and infimum in the opposite direction. So I'm looking at the infimum of upper sums and I'm looking at the supremum of lower sums. And then definition. If LF equals UF, say F low integral. And integral ABF x dx equals whichever one. So if these upper and lower the sum is actually the limit, then we say it's the limit. But the conclusion, which makes sense afterwards, is that these are actually the exact same thing. There is absolutely no distinction between them. So the theorem F is integral and only if Darboux integral. And the integrals are equal. So for this reason, you really can't take either of the definition. And the name Riemann and Darboux is really historical. So yeah, we're saying this is usually, I feel that saying usually. In my experience, this is typically the definition that we teach in our real analysis course. But somehow, if you think about it, the idea of treating it as a limit of an arbitrary family of partitions is more natural if you're learning limits for the first time. But this is much easier to work with. Absolutely, this is significantly easier to actually do computations with. You can go ahead. But the key then is the key point that I'm trying to make is that there is a important and subtle distinction between the partition and the tags. The partition is a way of subdividing the domain such that over it you're measuring the weight. Of course, I'm very worried. You're measuring this sum. Take certain sums. This somehow measures domain, or how much of the domain we're actually measuring. And this tells us the contribution of the function, in a sense. But these two things should somehow be considered separate. However, if you consider the definition, play around with it a little bit, you'll quickly come to the fairly clear theorem. If F is Riemann integral, of course I could say Darboux integral is the same, right? Then for any sequence of partitions, P n with absolutely any sequence whatsoever, such that the mesh was 0. The Riemann sum will always equal the limits this is some data for granted a lot of the time. If you know the function's Riemann, then you can take literally any sequence of partitions with any sequence of tags, so long as the mesh is vanishing, and you end up with a bracket. What implications does this have for this distinction over here that I'm trying to do? Well, this statement right here, that the mesh has to go to 0, saying that this part has to vanish, and sometimes it's not going to vanish, but the maximum of these differences has to be smaller and smaller and smaller and smaller. But I haven't said anything at all about the TNs. But the consequence of this, what you want to take away from this is that the choice of tags, the TI in here, is completely irrelevant. It's kind of silly that it doesn't matter which tags you pick. As long as you know that the function, the function is actually integrable, and you have a mesh that vanishes, your partition does not depend. Your sum will not depend on the choice of tags. Yeah. I want to pause here because we have a comment to make about pointers as relevant, and I just think I'll let him say the whole thing. Yes. This will take sure.
Yeah, please. Of course, I have to say a few words with numerical analysis right now. So the whole point of this choice of guide is completely irrelevant, but about numerical analysis. So just as an example, this quick quadrature formula, or that's all. And I think we need a drawing at this point. So we have our function that is doing some crazy things. So we have A and B, and it's doing things like that. It's continuous. And basically, we're doing this partition. So let's say that it's equidistant. We have x1, x2, x3, x4, x5, x6. All right. So we split the function and the interval we integrate on in partition. And what we do is that we choose a tag in each like here, and we choose the tag that is on the left, like that. And what we've been seeing is that the sum of the areas of all these rectangles, whatever the tag that you choose, if you if you increase the number of xi so that the length here goes to 0, but it does not matter. It will always give the area below the function. That's what we've been doing. In numerical analysis, we know that there are many ways to do this. Like this is the exact worst method ever, but it makes sense, and we will use it. So we like it anyway. But it's the length rectangle question. So I will not talk about the efficiency of all the quadrature formulas, but there's a question of order, and we know that you see that this one is exact if the function is constant. the function is constant, whatever option I take, it's exact. That's of order 1, because it's exact only for polynomials of order p minus 1. Or p0. Okay. But another one that we won't see right now, I chose the same function. Same is the midpoint. So basically, I take the point in the middle and I draw my rectangle here. So it is completely irrelevant. If the size of the mesh goes to 0, it's the same. From the numerical point of view, though, this is exact if the function is constant. This is also exact if the function is linear. Just to prove it, let's just do a small example. If the function is linear, take the midpoint, you cut this part here, and here inside, and it's exact, right? So the same in this method has all the tools. It's better this way. You get those nice theorems, nice estimates. The point is, why don't we continue like this? Because for stochastic integral, all of these are different, completely different. This will be called the integral. This will be called the integral. This will be fantastic for probability. This will be fantastic for differentiating functions. Just saying, we will talk a little bit more about this from time to time because it makes sense. And another thing I wanted to say that in creating measures of higher order, and then one is going to do a stochastic integration is its relevance. Only the first and second order are important, the rest we don't care. And we got that here for orders. Yes.
Okay, so this is exactly the point that it's often taken for granted. Tagging does not matter for Riemann integration. As we're trying to allude, it will matter a lot for stochastic integration. Let's go ahead then and generalize one step further. Okay. So the integrals that appear in stochastic sense are against the still unintroduced Brownian motion. This means that we have to have a notion of integrating this, a path. So, what first of all, the Riemann Stieltjes integral. Maybe it's a little bit less familiar. I don't think this is used for real analysis course, but it's definitely introduced in a measure theory course, yes? Yeah. I know DDA told me that he was able to talk about the Lebesgue Stieltjes integral in his measure theory course. Anyways, okay, so Riemann Stieltjes integral. What's the idea here? So, wants to introduce some G and define the integral of a to b of f of x dg. We want to understand what it means to integrate f against g. So, of course, we want our definition to agree with the idea that dx should just be g of x even if what if g, keep looking at the eraser here. What if g is somehow more complicated than that? Well, what this should do is somehow this function should affect what we mean by weights. If g of x is some monotone increasing function, then we really want to think about this. What we'll say we want is to let our Riemann sums to go from being this expression to g of xi plus g of x. So what does this accomplish? It somehow says that G determines how much weight should be given to the domain. That's how I want to think about this. So here, when we're integrating f in this the standard Riemann sense, we're just saying that over each subinterval just has the weight of the length of that subinterval. But in this, the subinterval now has the weights given by this difference.
Could this difference, the weight given be negative?
Yes. So what I drew here, and what I was starting with, is the idea of a monotonic function, in which case it's not. So if G is, I'll say monotonic increasing. Okay, so we're all familiar with this. I just mean that G of xi is always greater than G of xi minus 1. E is greater than G of A is less than B. If G of monotonic increasing, then of course G of xi minus G of x minus 1 is positive. And this actually all makes sense. There's no concern. Then if we say that R, the integral from A to B, f of x, dg of x, should somehow equal a limit of partitions as the mesh of the partition goes to 0, like this. Here, I'll try this. 1 m ti g one. If I say this, this will be well defined. Here it is. This is well defined in the same way, same sense that we have. So what I mean by that is that, we get two approaches. The Riemann integral is the epsilon delta limit definition, or the Darboux integral, the upper and lower limits. If your G is monotonically increasing, and I should say bounded, or let's just say continuous, something like this, then this all makes sense. This works just fine. But what happens if it's not monotonic? What if G is continuous? It's not
And of course, you don't even, I mean, the piecewise monotonic will be fine.
Yes.
This is,
Yeah. Yeah, so I'm being intentionally a little bit vague, trying to focus on the component. I think the most general that we could make this acceptable for is piecewise continuous at this level. Okay. Let's talk about how far we can push this. So we have piecewise continuous function, continuous field, but it's not monotonic, so it can be oscillating. So our picture for G looks something like this. So what happens now? Well, on this variable, actually, perfect. We're going to have that G of x1 is apparently greater than G of x2 is negative, right? Demonstrate this. This can cause problems for the convergence of something like this. So you can go through and play around with convergence sequences or convergence series. So the conclusion that we come to is we need G to be bounded variation. So definition. The variation, I suppose, on a variable of the function G is equal to the supremum across all partitions, possible partitions of the interval B of the absolute value of the sum and the absolute value G I minus G vector I. This will be called the variation, probably the one variation, but we'll call this just G. And we'll say that G is a bounded variation, this is finite. But what is this expression? I probably do need to set up some longer from arrays. The idea goes something like this. That's the function G. And by trying to find the supremum of such an expression, it means I need to find a subinterval that, or a subdivision that somehow makes sense that this absolute value is as large as possible. You can tell visually in this example. This is A and this is B. What you want to do is find the extreme values. This one, x1, this would be x2, x3. Because if you do this, your first subdivision here plus the height difference from here to here plus here to here and to here. So you can see visually for something like this, choosing the subdivision that catches these peaks and troughs maximizes the variation. So the variation of this picture visually should be the sum of each of these height differences. And fundamentally, this is what a variation does, commutation variation. The reason I take supremum is because of exactly the type of functions we want to avoid. Let's say, for example, f for g of x is going to be equal to the sine of 1 over x, and our interval is going to be so here let's make it so it's actually so 0 is less than x. Let's say 0. You seen this function? I mean the picture. It doesn't spring to mind. 0, we have 0. Oscillates. Of course, I can't draw this because there's in any interval from 0 to any finite number, there's an infinite amount of oscillations here. But this function is continuous, though, right? Because, yeah, okay. I'm going to cheat. Close enough. So the point is that if we tried to integrate against this due to x, we would have a problem because of how many oscillations we have here. It's varying up and down too fast. That means that the variation here would be infinite. This is precisely the type of function that we can't integrate against.
It's not clear to me that it's continuous.
It's not continuous. I shouldn't say this.
Okay, I have an example of something continuous that has a bad behavior. Yes, typically this. This is bad. This is the Brownian motion. This is one realization of a Brownian motion. This, the bounded variation is not bounded. I mean, the one variation is not bounded.
Fine, I can say this. The problem is we don't have a definition of this function.
X times the minus 1 over x.
Yes.
Written, sir?
Yes. So if you take this function,
Yeah, I think it's
there we go.
yeah.
So we have infinitely many oscillations here, but everything also converges to a close. This is continuous, yes. Yeah, it is a bounded variation. This one, even though it does convert down, this it's less obvious that the variation this is it's a little trickier, but I'm fairly confident. The thing that we should bear in mind is the kind of curves that we will deal with, which are much trickier to define. Although they are continuous, they also have bounded variation. So we will run into solving this issue. But the Riemann Stieltjes integral actually makes sense as long as we have bounded variation. So I can make this clear.
I think this one is bounded variation because it's Lipschitz, right? Although it's not. No, it's not. It's not Lipschitz. So I think no. Yeah.
If you can bound the variation from below by the sum of 2 over n. Or if you pick the
You're
talking about
an expert in these things because I've been doing
I'm no expert at all. If you pick the top and bottoms, and then you have a sequence going through the integers,
Yeah.
then you sum 2 times 1 over n.
Yeah.
You will get the difference, and that will something like that. That will do it.
Yep. I agree. Good job.
Okay. I really didn't technically define this. I just mean that that are interval. This tolerable, believable. Yeah. I think you can actually make this a little bit stronger, which is quite fun. If f is continuous on this on the set of discontinuities of G, then it turns out that this will actually make sense. Just like this a little bit. Okay, so this integral, the Riemann integral, will be the model for our stochastic integral. The idea when we get to this chapter would be to build a stochastic integral by following this model. The problem is precisely that I'm making it again, this is the Brownian motion and other types of patterns that we will want to integrate against don't have bounded variation. So the stochastic integrals are precisely the way to overcome this and make sense of how do we deal with the passive variation. We also alluded to some and passing. We've heard about rough paths. There's a talk last semester. There's people who work on it here. The point of rough paths is to understand how there are higher order variations and what happens when those higher order variations are also unbounded. So the Brownian motion that we'll be seeing is unbounded at this level, but it's bounded in variation. Okay. We should also take some time to review measure theory because some people have seen it, some people haven't, and we're going to need a lot of measure theory, at least as a foundation. We're also going to want our friend Lebesgue integral. So just some quick definitions. So space, I would take from the set X. Subsets of X on the collection A. I'm using the curly X to try to collection A. Subsets of X called algebra. If one null set is an A, two A is closed under countable intersections. And complements. So there are various other definitions, and this implies a whole bunch of other statements right away, right? So if A is closed under complements and the null set is in there, then of course the whole set is in there. Also, if it's closed under countable intersections and complements, then it's also closed under countable unions. So there's a lot of different things you can say, and you can also take some of the other ones as definitions. But we need these statements as a minimum set. It's fine for us. We say X is such an A, measurable space. And then unmeasurable space, map mu, which goes from X to from A. Unmeasurable numbers from infinity. Such that the measure of the empty set is 0, and we have countable activity. Countable union. Right, for of course AI means a countable collection of sets is called measure.
They cannot intersect each other.
Sorry, yes. That's a good one. If they have non-trivial intersection, we need some additive, it's less than equal to, but this isn't sufficient. But it's sufficient to define measure. I can just say this. I think I can do it with that.
I think it's easier to use the joint.
I trust in this also.
I think you need an extra assumption because it's going to be correct.
The point, of course, is that if you have disjoint sets, the measure of their union should be the sum of them. And this should hold for up to countable collections. I keep saying countable because we're avoiding uncountable collections. All right. I'll say. Also, yeah, I said measure. Measure space. A couple times it'll be relevant to just know the difference between measurable and measure. Measure means you have a measure assigned. Measurable means it's the space with the sigma algebra, but not necessarily having a measure assigned to it already.
We could, there doesn't exist a measure on
You can also take a trivial.
Yeah.
You just measurable set to 0, so a measure always exists. And you can also prove something better than that. Okay. I also note that all measures are always complete. What does this mean? Given a measure, measure space. Set. Okay, let's call this X. U. We can extend to X, A bar, mu bar. This is a technical condition, but it's important to assume. Such that if such that let's say one we have this string extension. Two, if A is measurable in A, then the measure of the new measure is the same. Okay, so these two statements say we're not losing any information. The information says the measurable sets that were measurable before are still measurable, and the measure doesn't change. But 3 is B is a subset of A, which is measurable, with the measure of A equal to 0, then B is now measurable, and the measure of B 0. So what does this say? This says if there's any set that was measurable and it had measure 0, then all of its subsets B are now measurable and their measure is 0. It looks maybe a little messy, but really all I'm saying is that you can with any set of measure 0, all of its subsets also have measure 0. As a technical definition that I remember when I saw this in measure theory, I forgot, I thought it was kind of silly, but it actually makes a lot in probability theory. So yes, we call this completion. And we will always assume all of our measure spaces are complete. So you never need to worry about anything.
So what does it mean that it's complete?
It means that it's equal to complete. I apologize. I will say that a measure space is complete if it is equal to its completion.
It was not clear to me what is the completion because they have been extended. You say
Yes. So I'm saying if any measure space, you can extend it something like this, where all of the subsets.
you just have to extend it somehow. Yes.
Yeah, I mean, you literally just say, take if B is any subset of a null measure set, it's a measurable measure 0. We call this a new space of completion. And I'll say that this set is complete if it equals its own completion. So there's nothing to do.
And all you need to do is to take into account all subsets of all things of measure 0. So
Yes.
Yeah.
Exactly. Yeah. So basically, whenever you're in anything, if you have a set of measure 0, you can always assume that any of its subsets are measurable within it.
Yeah.
That's just an assumption you can make always, which is very relevant, remarkably. Maybe this is just me getting hung up. I remember spending almost a week on homework problem once in a probability theory course. Not being able to prove it because I forgot this system. All right, so we have these foundations. Talking about probability theory, we will do a review of all of the necessary components of probability theory, stochastic analysis, practical processes next week. But I will give you the basic definitions. It's measure space. Omega P. This is literally just an anagram for that. It's just different letters for the same thing. Okay. So omega is our space, F is our measurable sets, P is our measure. It's called a probability space. It's the measure of the entire space is equal to 1.
I don't know if you included it in the definition of measure, but I checked it. You have to add that mu is positive and cannot be infinite.
Then those are both included. So part of my definition of measure space is not a sign of measure, so it has to be positive.
Okay.
So we're insisting on this. Measures must be positive. There's no negative measures.
So you took
And it being finite is guaranteed by this
Yeah, yeah, yeah.
subset rule. So if you have a measure space, its measure is always positive and non-negative, we should say, it'd be 0. And the measure of the entire space is 1. Necessarily, the measure of the subspace must be necessary 1. We're done. Okay, this is that's why I like to set this way. Okay. So honestly, if you ever want to upset a probabilist, tell them that all they study is probability theory on spaces of finite dimension. It's an entirely great probability. It's a gross oversimplification, but it's fun to say.
I agree with final statements that people get really angry.
If you never really want to upset a problem,
You start saying something, but this is only.
Yeah.
only work with finite measures. I see. In this setting, we change our limitations, of course. We say that omega is the set or space outcomes. F is this is the space set of events, at least the measurable events that you want. And P is probability. So we'll go into this much more depth next week. But is anyone who hasn't seen this? Or maybe I should see this. I mean, the whole point of this is just this space omega is generally considered somehow very abstract, sort of unknowable. It's supposed to be the set of all possible things that could possibly occur. It's an extremely absurdly large space. But the point is that F tells us precisely which types of outcomes can be measured and understood. So it's really F that you want to think about. An outcome in omega is generally a very abstract thing. And probability hopefully goes into intuition for putting this. Okay. So in practice, what this means is that whenever we're talking about random variables, probability things, we're working with finite measures. But it will still be necessary to think about signifying signified measure spaces. Because stochastic processes live both as random variables in this sort of space, but as well as variables over, let's say, the non-negative real line, where we're considering that to be time. So when we're doing stochastic analysis, we need both of these things. We can't just limit ourselves to this. Am I doing time? I don't want to cover too much. Overmuch. Yeah, overmuch. The last thing I want to cover then is Lebesgue measure, which gives us precisely this other integral. I'll be quick. No. Right. So what we do is we go ahead and say that R is reasonable. We want that measure an interval. Right. I'll put a little L for this. We want that the length of an interval should be what? E minus N. This is precisely what we say when we're doing Riemann integration, right? When we do a Riemann integral, we're measuring against subintervals and saying the length of each subinterval is just the difference between lengths. The problem comes when you try to define the measure of more complicated sense, right? So for any subset of I, we can define who's like this. All right, then yeah, the interval. So infinity is it's gonna be a countable sum. Countable lengths. Where we has to be contained in the countable union. And our intervals. So maybe it's clear, but what I'm saying is that if you take literally any subset of R you can always cover it with a countable collection of intervals, right? It should be clear because we know that the topological properties are. You take the sum of the lengths and then try to find an interval of this. This should make sense for a measure R, or an outer measure. Outer measure. The technical problem here is that the power set of R, that is the set of all subsets, is not a sigma algebra, right? Okay, so what we have to do is we need to find a set of measurable subsets of R. So we say that the subset of R satisfies the if for any subset of R, the outer measure of A is equal to the outer measure of A intersection B plus the outer measure of A intersection B constant. Clear? What this condition require? So what we want is that if you pick any set, you can find its measure by intersecting it with your E and intersecting it with the complemented summing of the two. Turns out that not all E satisfy this, and in particular, collection of sets E satisfy the condition. It's a sigma algebra. And these we refer to as the Lebesgue measurable sets. So I call these A. Then R. These sets is a measure space. We call this, and I should maybe explicit here. Lambda is just lambda star restricted to this set. Distinction here. So lambda is just lambda star restricted to this. And measurable set. I'll just say Lebesgue. This is fine. This is what just a month and a half of measure 15 minutes. Sorry.
Maybe keep the example of Q to measure the measure of Q.
Oh, sure. I mean, yes. So this is fine. So we could say, I mean, maybe this is. I feel like everyone here probably knows this is why I feel silly repeating it, but sure, I'll just say this. Yeah, that's right. This is somehow the first big surprising result when you start looking at measures very properly. In fact, zero for any countable set. This kind of thing. I mean, it certainly matters, but I don't know how much more I have to say about this. I do want to, however, define the Lebesgue integral and compare this then to the integrals that I had spent one time on. because it turns out we also need Lebesgue integration. So right. Let's define the integral subintegral of f. We want to make sense of this. Or f here, some sort of function r, and lambda is supposed to be our Lebesgue metric. We want to know what this is. So the idea, so the integral, I'm just gonna put r here. Take all of the function. The integral against all of r, the indicator function of some subset that should equal the measure of that set. And we will often, okay. We'll then say that the integral of e f this. All right, so we want these statements to be true. We can take this as a definition. This is fun. If we're going to iterate against the indicator function, I should say e measurable. Say 1b 1. There. So good. So this is definition of what it means to integrate against a indicator function. We want this to be true, so we'll take this sensible if we move it this meant. So it makes sense of that other statement. We say the following.
The last one is just definition of integral release.
Yes, yeah. I just want to make sure. I just want to be clear what it means to integrate or subintegral. So I don't have to keep saying this. Yeah. I'm going to write all of my integrals against all of them are. Whenever we talk about integrating against some subset E, what I mean is that you restrict to the indicator function. But I still got to make this a little distance. So if f is of the form f is equal to some countable sum, some constants times the indicator functions. Disjoint all points and the alpha I are all real numbers. S call F simple. Number of measures. You remember that everything you prove something for simple functions and then the rest follows, right? And then we set the integral r of f lambda is simply equal to the sum from I equal 1, then I suppose alpha I measure. Yes. Next. If they're not disjoint, as long as the intersections are simple enough, you can always rewrite it in this form. The intersections are not simple enough, well, then we get into complicated things, right? So the key step, the most interesting one, this is just linearity. But yeah. What we say then is f equal the set of f. Write this. Given I see where I'm sorry. I didn't define measurable functions. I need to do it right. Definition f from R is measurable. This would be the proper. I apologize, I keep trying to step backwards. Given measure spaces, X with A and Y with B. Function f from X to Y is called measurable if for any measurable set in the range, f inverse of this is measurable in the range. Yes, it's the same idea as the continuous function in topology, that creating open sets. Okay. I do this then because given a measurable function, f R. So here, X is a measure space, R is equipped with, let's say, taking out what I said before. Then we can define F be the set of simple functions that are pointwise above F. I'm saying we have some measurable function, consider the set of all simple functions, and those are the simple functions over there. And then we can define an integral using these. Then the integral for R and suprema. So that's the integral for R. Yes. This is all. So I had to go into a bit of a segue to define measurable, because the key step of the proof here is to show that this sort of supremum argument is well defined, so long as we're restricting to a set like this of functions that are dominated by a measurable function. And this is defined as before, right? Because f tilde is simple, and thus we can write it as the sum of anything times the measure from a bit of space. I like to hear it. Once the thing is that this is actually acceptable if this is positive. I don't know. Then what happens is if you want if you have a measurable function that goes to the entire real line, you split it with positive and negative parts and subtract them. Okay. I'm very much skipping the technical details of approximation methods. But the point is that this kind of integral makes sense for measurable functions. Okay. We also have all this technical, we've done this sort of technical approach, but are you familiar with the difference, the fundamental difference between this and the Riemann integral?
We find the range instead of the domain.
Yeah. We got a picture.
Yes.
The point is, when you do a Riemann integration, as we drew this picture several times, we subdivided this integral and we summed out the little rectangles, right? And we sum these up. The exact complement of this somehow is happening. When you're doing Riemann, or when you're doing Lebesgue integration, you pick a height, you subdivide it like this, and you build these rectangles. That's like this thing, and so on. Drawing is very important. But the point is that somehow we're subdividing the range, and this is achieved by the formula that I erased here, where we consider the integral of simple functions. Because when you integrate a simple function, it's precisely this. You're subdividing the different heights and then measuring the underlying measure of the space. This is unfortunate, poor choice. Yeah, there's a picture.
No, it's just that it's okay.
It's okay, but
It's not.
I sort of why this idea is so much better.
It's not much better. It's not, because you can extend the definition of Riemann integrable functions, and you can create some functions that are Riemann integrable and not Lebesgue integrable. And no, you
This is extremely misleading. That's only true if you extend to infinity. If
Yeah.
you're talking in complex sets, Lebesgue integration is strictly that. So let's finish with this. Okay. So the issue, the fundamental issue with Riemann integration, I'm insisting that we stay confined to compact sets.
Okay.
Okay. So constrained to compact sets, I can make the chalk statement. If F is Riemann integrable on some compact set AB, then F is Lebesgue, okay? Compact set AB. If you want, I will give you an example where there is a function that is not Lebesgue integral, but is Riemann integral on the whole Riemann. But this is pathological. The reason this happens boils down to something like, I think you can see clearly with the example here. Let's let F equal 0 if X is in the rationals, and 1 if X is in the irrationals, right? The irrationals. So what does this horrible looking function look like? And we can't get it yet, but let's pretend. Looks something like this. Here's 1, here's 0. This is fine. If I try to take the Riemann integral, we'll just say integral 1 of this function, it does not exist. And why doesn't this exist? Well, whenever you take any partition, so you choose a partition, right? So just of the interval from 0 to 1. And whatever partition you choose, you pick some boxes. Every single one of these boxes will either have height 1 or height 0, depending on your tack. And as the subinterval gets smaller and smaller, your tacks can vary quite a lot. I mean, nominally they should vary any way you want for a line interval. But on any subinterval, you can always choose a real irrational or a rational, and everything is always going to be more. You can always choose a set of tags that has an infinite number of ones or an infinite number of, any you want. So this cannot make sense. However, if we go the other way and try to do a Lebesgue integral with this, then we did 1. And the reason is any approximating simple function will tend to that. Because we're not measuring the points and then trying to afterwards measure the domain. Instead, we're finding what our simple function has as a height value and then measuring the underlying set of this. So fundamentally, this is really the measure of the irrationals interceptor. So fundamentally, what the Lebesgue integral does that the Riemann integral fails is to properly capture the maximal notion of measurability. Riemann integral fails whenever the underlying domain is sufficiently complicated. Yes. If you want this example, I'll give it a like this example. This statement is not true on the whole real line. And the function is, I have to give a reminder of this 20 minutes before we start talking. Is this. So what this function does, assume the integral away from 0. If you want, you can extend it to 0 by making this. Okay. So we have a given function. Looks like this.
It starts at 0. Which
Excuse me.
no, it's okay. It starts. Oh wait.
No, it's one. It's one.
Yeah, it's okay. It's okay. Yeah, sure.
Well, this is fine.
Yeah, it's fine.
So this function, if you want to integrate it over 0 onto infinity, yeah, this doesn't exist. And the way to see this is
Are you talking about Lebesgue now?
yes, the Lebesgue integral of this is not one of the time. The reason you can prove this is that you take the absolute value of this. It's a simple fact to show that if the absolute value of a function is Lebesgue, a function is Lebesgue integral if it only gets its absolute value is Lebesgue integral. Not only if. And what happens is that when you measure this, the underlying measure is R, essentially, minus this unaccountable set of the zeros. So this doesn't work. I should say positive infinity.
No, not even. No. It does not have any sense.
Yeah, I'm gonna stick it as good. But this does exist. It's what if I squared over 6 or something. Someone's gonna prove this. This is something. The reason for it is that this is an improper integral defined as a limit. Right. The definition of this is you put b here and the b tend to infinity. So you write this as limit as n goes to infinity of the sum from I to 1 to n of integrals of the form n pi n plus 1 pi of this, right? And it turns out that the oscillatory nature of this means that these cancel in a very nice way. And so the Riemann integral actually does make sense here.
I'm also doing it's shocking. I think to make this thing. It's a bit shocking.
Yeah, I know.
Exactly.
Yeah.
Okay, it's the same function comes up in Reynolds all the time, and it means that if you're working with the Lebesgue integral, then you have to be careful with things like what I call this formulas of the integral of the function.
The main problem with Lebesgue integral is that you need your functions to be L1 basically.
Yeah.
They're
That's the definition.
yeah, exactly. Yeah, the absolute value has to be finite if you integrate it. And that's the problem because you can typically create these kinds of functions.
But you know, so when
If you integrate absolute value, it must be finite.
Yeah.
yes, yeah, the absolute, if the integral, the absolute, okay,
You can define the LP spaces and then you end it here.
Could you fix the Lebesgue integral by saying that you take all compact subsets and you
you can there's something that goes wrong here. I don't know. I'll be honest. But no, if there's some reason it doesn't work. And this is related to the fact that Lebesgue integral makes sense that the Lebesgue integral is measuring E instead of Lebesgue measuring sets on R. So something precisely about this, the Riemann integral misses what makes this work out. But, you know, we can define this. We say F is 1. Like if the integral over R that's next, and there's a statement that says the integral of d lambda exists if f is integral. For any e. This sort of thing. You can play around with these sort of things. This is if you really want to know the true story, but you should take everything. Yes.
Okay, it's just such long time ago.
Exactly. Okay. Yeah. Which I really hope will be, of course, sometimes. Okay. And we'll hopefully in the next few semesters there'll be an entry for a second. My understanding, next semester or one after, it should be.
I think in 1 year, because it was, I don't know if it's still, but it was a mandatory course in mathematical analysis. So
Yeah.
it has to be at least once every 2 years.
The reason I'm excited about this is a chance for me to teach it. It's talk. And yeah, so I think I'll leave this in here because what we have to do next is actually now take all of the ideas and explain what random variables are and explain what stochastic processes are and all of the interesting probability things that you miss when you make this joke. The probability theory is measure theory and not finite measure space. I'll say this comment in passing. We all know that we typically assume you can interchange the order of integration, right? And the definition, the statement of this is called Lebesgue's theorem. The technical thing that we need for this is that Lebesgue's theorem holds for measurable functions, non-negative measurable functions, on sigma finite crop spaces, by which we mean that the measure is sigma finite. This is never a concern for us because our spaces are a probability space, which is actually finite, and R, which of course is sigma finite. So we never, in this course, whenever we're dealing with the interchange of integrals, we can assume we will everything's fine. I was going to say a bunch about this, but I think I said enough about that here.
So next week, I will present some probability, the basics. And we will,
What are we think? I mean, twice once a week is not only Friday.
yeah, every Friday, the same time, at 12:15.
Okay, if you say something more, I mean, you have to work very hard to demonstrate the existence of non-measurable sets.
Yes.
To me, every subset is measurable in practice.
Yeah. So I want to go over this to make sure we're clear. There are plenty of technicalities hidden behind what we're doing, but thankfully this is basically all.
Yeah.
When we encounter technicalities that are a problem, we will address them. Yes.
I mean,
primary technicalities can be
the biggest technicalities are not with the measure theory. They're with probabilities, the Borel-Kenton dilemma, and we will try to avoid all these things.
Yes.
Um,
It is good to keep in mind when we finally do next week we define random stochastic process. This is both a random variable, unless it is measured over a probability space, but it also is over the non-negative real numbers because this is somehow a process that changes time. In which case we'll have the Lebesgue measurement for our sigma.
So I believe that it's correct to say that if you don't believe in absolute choice, then all subsets are measurable. That's, I think the only way to construct a non-measurable set is to apply an absolute choice.
oh yeah, I've seen
Yes,
this.
yes,
Yes.
funny example.
Yeah, the mentality, but I prefer this. I don't know.
I think it's proven that you cannot do it without absolute choice.
Is there a proof of this?
No, but it's written in the black book.
It's not proven.
No, it is proven that if you don't have the absolute choice, then every subset of R is measurable.
Is it proven that every subset of R is measurable, or is it proven that you can't construct an unmeasurable?
Yeah, I think that's the point. You cannot construct a non-measurable set without.
But this doesn't disprove the existence.
Construct, but construct, no, it doesn't exist.
Okay. This is subtlety. I'm not sure.
Yeah,
I
that's
100% agree that there's no way to construct a non-measurable set without the absolute choice. But does that prove that there does not exist a non-measurable?
No, you're completely right. There's a difference between existence and construction. Definitely, there's something there.
And I'm not at all read up enough to be able to say. So.
I think I will stop the video here.
Yeah.